Okay, welcome back Science 10s to our next lesson. This is 5.2 and we're going to be looking at motion. Okay, so from your experience in life, you're pretty familiar with what motion is and what motion isn't. If we have an example like this is movement. This is a lot of motion. But an example like this is not. We are not moving in this case. So we know and understand this, but how do we actually tell and calculate motion? Well, kind of related to last lesson, we know that if an object starts in one position and then changes its position to another place, that it has moved. So movement has to do with change in position. That's what we looked a lot at last lesson. But now we're going to be looking at, well, if we have a vehicle and it changes its position the same amount and does it quickly compared to another vehicle that does it much more slowly, I mean, its change in position was the same, but there's something different here. What's different is the rate that they changed their position. So the rate of change in position is what we're going to be looking at in speed and velocity. Okay, so here are terms and what we're going to be comparing in this lesson. Speed and velocity. Speed is a scalar quantity, which remember from last lesson means it does not worry about direction. And it's looking at our other scalar quantity of distance over time. Velocity is kind of the opposite to that in that it is a vector. Think of velocity, vector, those start with a V. And this is looking at the vector quantity of displacement over time. So our formulas here are going to be, for speed, S is equal to our distance, which we just said was d, divided by time. This is similar to rate of change, which you looked at in math. Something divided by something. If we have the distance in meters divided by the time in seconds, our unit will be meters per second. Really similar for velocity. So we're just going to write V is equal to d over t. But remember, this isn't distance, this is displacement. So I have to put that triangle and an arrow, say that that's a vector. This is going to be looking at our velocity, which has an arrow as well, because it's also a vector that's considering direction. Now, to be most correct, I should probably put a triangle here as well, because we're looking at the change in time. Actually, in both scenarios, we're looking at the change in time. And for velocity, we could be measuring our displacement in meters as well, divided by the change in time, which is seconds. So we'll get a unit like meters per second. You could also get this in kilometers per hour, which is pretty common. So if your distance or your displacement is measured in kilometers and you're measuring your change in time in hours, you could get a unit like that in kilometers per hour for either velocity or speed. So these terms are really similar. It's just the vector and scalar quantity. And often for this course, they're going to be the exact same number. So let's look at an example of when they're going to be the same. If a person bikes 20 meters east in 10 seconds. So they start right here. They go 20 meters east in 10 seconds. We're calculating the speed. That would be our distance. We went 20 kilometers. 20 meters. In 10 seconds, divided by 10 seconds, and we would get 2 meters per second is the speed. Now, if we look at the velocity, we're going to put the displacement. In this case, they ended up 20 meters from where they started, so 20 meters divided by 10 seconds. Now, the only thing that changes here, we have to consider direction. So 20 meters east in 10 seconds gives us 2 meters per second east. And it's important there that we are considering the direction. Same number, just considering the direction when we're talking about velocity. For that reason, we're often going to be using velocity because we often want to know where it's going or where we're traveling. But the value pretty much stays the same. The places where speed and velocity are different is if we have a changing direction. So a person bikes 10 meters east and then 10 meters west in 10 seconds. So they start here and go 10 meters east and then 10 meters west. Their speed would be equal to the total distance. They went 10 and 10, so that would be 20 meters divided by 10 seconds, and this is the exact same as we had before, 2.0 meters per second. But this is where velocity is going to change. Velocity is equal to their displacement. Well, they started here, came back, and ended up right here at the end as well. So the displacement was 0 kilometers or 0 meters. Divided by 10 seconds, well, 0 divided by anything is going to be 0 meters per second. So that's what the velocity is for this trip. Is that really that useful to say how fast they were going? Not really, but it represents an average velocity. They were traveling at 2 meters per second when they were going in the east direction. Then when they came back, they were traveling at -2 meters per second. I put the negative here to show the direction. We call this way positive direction that way, and then this way, negative direction that way. So now their average of going 2 meters per second in that direction and going 2 meters per second backwards in the opposite direction, that averages out to 0 meters per second. So it's not really good to look at the whole trip because their average was 0 because they ended up in the same spot. But knowing that at this point they're going backwards, negative 2 meters per second, and knowing that they're going forwards, positive 2 meters per second here is often important to consider. It's just the round trip average that sometimes isn't that useful, but that is what we get from calculating this velocity right here, looking at that total trip. So don't worry too much about those average velocity during the whole trip examples. It's mostly important that we know that direction matters for velocity. So another place where that would be important to know is, say we have this person and they're going to drop or throw a ball off of a cliff, and say they're going to throw it at 2 meters per second. If we just say the speed that they're going to throw it at is 2 meters per second, how fast is it going to be going after 1 second or 2 seconds later is really important on the direction that they threw the ball. If they threw the ball upwards at, let's call upwards positive, if they threw it up at positive 2 meters per second, that's going to start slowing down as it goes up because gravity is pulling it back down. So that would be if it was positive 2.0 meters per second, it's going to slow down and eventually come to a stop before it starts falling back down again. But if they threw it downwards at negative 2.0 meters per second, we're calling downwards negative, gravity is going to be accelerating it in that direction. So it's going to start going faster as it keeps going down there. So how its velocity is going to change in the next second or two is quite dependent on whether we threw it up or down. So that's why we often use velocity, because we are interested in what direction that object's going to be going. Okay, so just before we finish off this video, we're going to look at rearranging that formula for velocity. So we're going to consider two situations. The first one is going to be if there's a thunderstorm and there's some lightning. You may have heard before that you can figure out how far away the lightning is based off of how long it takes between time of seeing the lightning and hearing the thunder. So let's say if it takes 5 seconds between when you see the lightning and hear the thunder, how far away is the lightning? Well, to solve this, what we have to know first is that the speed of sound is about 343 meters per second. It changes a bit with the temperature, but it's around 343. So this is a velocity, and the direction that it's going is towards the person's ears. So I'm going to put v is equal to d over t. I'm not going to write all the triangles and arrows. We're just going to keep it simple with v is equal to d over t. And it's asking how far away is the lightning. So that's looking for the displacement at the top here. So how I need to solve for that is I need to know the velocity, which I do, 343 meters per second, and know the time, which I do as 5 seconds. So to rearrange this, I want to get d by itself. So how I'm going to do that is I'm going to move t to the other side by multiplying by time. This is the opposite of dividing, so it cancels out here. D divided by t and times t is canceling that t out. There's no effect of t, is times and divide. If I do that on that side, I need to do that on this side as well to make sure this equation stays equal. And so t times v is equal to our displacement. So I take my 5.0 seconds times by 343 meters per second, and I'm getting a number of about 1,715 meters. This is a lot of meters. I'm going to actually turn this to kilometers, just divide by 1,000. 1 kilometer is 1,000 meters. And it's 1.7 kilometers away. So that can be a useful equation to know for trying to figure out how far lightning is away from you. And it shows how to rearrange for displacement with our velocity equation. Now the next question is going to be, say that you are in a vehicle and you see a sign that says you are 70 kilometers from your destination and you're driving the posted speed limit of 110 kilometers per hour. You might wonder, how long is it going to take to reach your destination? And so this situation again is dealing with velocity or motion. It's important that we're going towards our destination. So I'm going to use v is equal to d over t. And we're going in a straight line to get to our destination. So this would be the same as speed as well, but I'm going to use velocity because it's good to include direction. We're going in the right direction towards our destination. And I'm going to ask to solve for how long it's going to take to get there. So that's looking for t. Now the problem with rearranging for t is it's in the denominator, and if we move the d to the other side like that, we would get t on its own, but it's going to be 1 over t. And that becomes a little bit complicated and seems to confuse students. So I say the first thing that you should do is if the variable that you're trying to solve for is in the denominator, get it out of the denominator. So I'm going to write v is equal to d over t. Solving for t, how do I get it out of the denominator? It's actually do the same thing that I did in that last example by multiplying by t. So times by t cancels there, times by t, now it's over here. Okay, so now I'm just going to erase those t's from this side, and now I have t is equal to, or sorry, t times v is equal to d. Now that it's no longer in the denominator, I want to get that t by itself, so I have to get rid of this velocity. How I'm going to do that is t is times by velocity, so to cancel that, I'll divide by velocity, cancels out, and divide by velocity on this side. Okay, so now I have t is equal to my displacement, which is going to be 70 kilometers, divided by my, my velocity, which is 110 kilometers per hour. You'll notice here that we're working with kilometers and hours and not meters per second, but that's okay because my displacement here in kilometers and the displacement part of my velocity, that measurement of distance is in kilometers as well. So as long as those are matched up, that should be okay, and we will get our answer in hours. So I take 70 and we divide it by 110, and you get an answer that is, it's about 0.36, kind of repeating, or sorry, 636, kind of goes on for a while. And that's in hours. Again, we don't really like to represent how long we're going to be taking to go somewhere if it's less than an hour. In hours, we usually want to turn that to minutes. So how you do that is you just times by 60 minutes to turn our hours into minutes. And there I'm getting a number that would round to 38 minutes as our answer. Okay, one last thing to put in here before we do finish the video. If you are given a number in kilometers per hour, and it's asking for you to look at something in meters per second or in seconds, you can convert between kilometers per hour and meters per second. All you have to do is you have to take your number in kilometers per hour and divide by 3.6 to turn it into meters per second. Oppositely, you just have to times by 3.6 to go to kilometers per hour. So for example, if you had 100 kilometers per hour, but the question said maybe you drove or ran or something for a certain amount of seconds, and so I want to turn this kilometers per hour to meters per second, you take 100 kilometers per hour, divide by 3.6, and you should get 27.7 repeating meters per second. So that could come useful in some of your questions. Anyway, I hope that made sense. Give those practice questions a try, and I will see you in the next video.